Here's to anyone who's ever looked up. The airheads. And the space cases.
Live long and prosper.
The flight fanatics. The armchair astronauts. And the casually curious. Here's to those who know the thrust in newtons of a Pratt & Whitney J75 turbojet engine. And those who silently ask, what's keeping this thing in the air? Here's to those who can list the name, mission history, and favorite breakfast of every Mercury astronaut. And those who've ever searched for, how does a toilet work in space? Here's to the people who knew a P-38 Lightning from a P-51 Mustang. And the people who thought those were the names of cars. Those captivated by the miracle of flight. And those who are just happy to make their flight. So whatever captures your curiosity.
We choose to go to the moon.
Or propels you to new heights. When it comes to the sky, there's space for all of us.
Good evening. I'm Chris Brown, and I have the true privilege of serving as the John and Adrienne Mars Director of the Smithsonian's National Air and Space Museum. Welcome to tonight's Exploring Space lecture. Tonight's program is the final in a series of 4 lectures exploring various missions that have returned samples from the moon, comets, asteroids, and one day, other planets. First, we discussed what we have learned from the lunar samples collected by the Apollo astronauts half a century ago. Then we told the story of the Stardust mission, which brought back samples of the comet Wild 2 in the early 2000s. Last month, we explored the ongoing science being conducted using the recently returned samples from the asteroid Bennu. And now tonight, we will look forward to another ambitious sample return mission that aims to bring back to Earth Martian samples collected by the Mars rover Perseverance. This endeavor will involve the collaboration of multiple space agencies, robots, and teams. I know we're all anxious to learn more about this bold mission. But before proceeding with tonight's program, it's fitting that we extend our thanks to the sponsor of the Exploring Space lecture series. Tonight's lecture is made possible through the generous support of Aerojet Rocketdyne and United Launch Alliance. Joining us in the audience tonight are Joe Cassidy from Aerojet Rocketdyne and Adi Basali from United Launch Alliance. Thank you, Joe and Addie, for your ongoing support. We'll give them a round of applause. And today is actually special, particularly for these companies, because the Starliner launch atop a United Launch Alliance Atlas V rocket took place and is expected to dock with the ISS tomorrow around noon. What a wonderful achievement, and congratulations. To those of you here in person, I hope you had the chance to tour the Destination Moon and Kenneth C. Griffin Exploring the Planets galleries before tonight's lecture. These spectacular exhibitions are 2 of the 8 galleries that have opened so far as part of our ongoing renovation of this remarkable museum, and we were pleased to share them with you as part of tonight's program. Now, I'd like to turn it over to my colleague and friend, Dr. Matthew Schindel, a museum curator of planetary science and exploration, to introduce tonight's speaker. Matt?
Thank you, Chris, and good evening, everybody. I'm Matthew Schindel. I'm the curator of planetary science and exploration here at the museum, and tonight I have the honor of introducing our speaker. Our speaker this evening is Dr. Meenakshi Wadhwa, Director of the School of Earth and Space Exploration at Arizona State University. Her research group is best known for developing novel methodologies to investigate the timescales of processes in the early solar system. Dr. Wadhwa has been involved in several NASA planetary science missions, including as co-investigator on the Genesis mission and as a collaborator on the Mars Science Laboratory mission. She has hunted for meteorites in the Antarctic, for which she's received the Antarctica Service Medal. Dr. Wadhwa currently chairs the Science Committee of the NASA Advisory Council and was chair of the NASA Curation and Analysis Planning Team for Extraterrestrial Materials Analysis Group. She also served as a member of the National Academy of Sciences Space Studies Board and its executive committee. She's very accomplished. Dr. Wadhwa became a fellow of the American Geophysical Union in 2019, the Explorers Club in 2012, the Wings World Quest in 2007, and the Meteoritical Society in 2006. In recognition of her contributions to planetary science, asteroid 8356 was renamed 8356 Wadhwa by the International Astronomical Union. You know, I think every speaker this year has had an asteroid named after them. I think we're doing something right. All right. So tonight, Dr. Wadhwa will talk about the Mars samples that the Perseverance rover has collected so far, the ones it's expected to collect in the future, and the scientific motivations for bringing these samples back to Earth. It is my pleasure to present Dr. Meenakshi Wadhwa.
Thank you, Matt. This is just a real honor to be here talking about one of my favorite topics in the world, which is bringing back Mars samples here to Earth. So I'm going to start here with just a brief overview. I'm going to talk a little bit about what is motivating us to bring these samples back from Mars. This is an audacious and incredibly bold mission, and it's difficult. And why do we want to do it? We're going to talk about what the status is of the current Mars sample return program. We'll talk about what the status is of the samples that Perseverance has been collecting so far on Mars. It's happening right now. And so we're going to talk about the samples that we've already collected and those that we're going to be collecting in the near future. And then, of course, we'll talk about what's next and where we're going in terms of Mars exploration and what we hope to gain from that. So NASA has invested incredibly for the last 6 decades in Mars exploration through a variety of increasingly sophisticated spacecraft by flybys, orbiters, landers, rovers. And the reason that we want to do this, of course, humanity has been incredibly fascinated by Mars for centuries, of course. But it's only now that we're able to actually go there and actually explore Mars as a planet. And of course, we know that it's our closest neighbor. It may have been Earth-like in the past. And so the hope is that we'll learn something perhaps about our own planet, our own origins, from going to Mars and bringing back those samples and bringing them back here. And so we're hoping that we'll be able to bring these samples back sometime within the next decade or so. So Mars sample return, this is going to be, as I mentioned, an ambitious mission, the first sample return from another planet. It's been a priority, though, of the scientific community for at least since the 1980s. I'm not going to say when I was a graduate student, but I've been dreaming about Mars sample return since I was a graduate student. And it's always been just about a decade away. And at this point, it actually seems like reality because we are actually collecting those samples that we're hoping to bring back. And we're hoping to bring back within the next decade, but we're actually collecting those samples at this point, so it seems more real than ever. And so the reason why we want to go to Mars and study Mars, of course, is because we know that the oldest life on Earth started sometime like 3.5 billion years ago. There is hardly any trace of that past that is currently preserved on our planet. There's something like less than 1% of the Earth's surface that is 3 billion years or older. And in fact, if you think about 4 billion years, there's only these tiny, tiny grains, these minerals called zircons, which are maybe even less actually than the thickness of a human hair. That's all that's left of anything that's older than 4 billion years here on Earth. But on Mars, more than half the surface of Mars is older than 3 billion years ago. And we know from having studied it through the systematic exploration that we've been able to do on Mars, that Mars was actually quite Earth-like, perhaps, in its ancient past. So 3.5, 4 billion years ago, it had these habitable environments, and life may have been flourishing there at some point. We don't know that for a fact, but we're hoping to find that evidence when we bring back these samples. And so that is the reason. I mean, we want to be able to go back to places in our solar system, and Mars is a prime example of that, where life may have developed. And that could give us some clues about how life may have developed here on Earth. And so we're really looking to understand our own origins in this quest. And so the first billion years or so of planetary evolution, as well as the possibility of life originating, that's all preserved on Mars, and that's the real motivation for going there. And so the big questions then, those questions relate to understanding how rocky planets form in our own solar system and beyond our solar system. We want to understand the history of, the magnetic field on Mars. That, of course, has an impact in terms of the habitability of that planet and how that evolved. We know, for example, that the Earth's magnetic field protects us from radiation from solar wind and cosmic irradiation. And we think that Mars actually had an active magnetic field sometime in the past, probably close to about 3.5, 4 billion years ago. And what happened to that magnetic field, and why did it turn off? We want to understand the timing of major impacts of big volcanic events, all of those kind of planetary scale processes that shape how planets, rocky planets, evolve and become habitable. We want to understand the climate history on Mars. We want to understand what happened to the water that was once flowing on the surface of Mars, that once had standing bodies of water on the surface. How did Mars's climate evolve over time? How did the atmosphere evolve? We think that it probably was very much thicker than it is today. Of course, today Mars is extremely cold and dry, and with a very, very thin atmosphere, about 100 times thinner than that of the Earth. And in the past, though, we think that it had a much thicker atmosphere. So what happened? How did it evolve to where it is today? And we want to understand, of course, the history of water on that planet, as I said. In all of this, of course, we want to understand the potential for the development of life on Mars. Was Mars ever inhabited? That's the big question. The question of, are we alone in the universe? I mean, that is the fundamental question that we're trying to answer. And that's the one that we hope to be able to address through exploring Mars. We want to understand how prebiotic environments on habitable planets, what do they look like? When and where did life first develop on Earth itself? Of course, I mentioned we are hoping to learn something about our own origins if we understand how life develops in other places in our solar system. What kinds of conditions prevailed, what were the raw materials that contributed to that. All of that, these are all sort of the big picture questions that we're hoping to be able to answer when we explore and we study Mars. Now, we can try to answer these questions by continuing to do the kinds of exploration that we have been engaged in with landers and rovers and orbiters, but why do we want to bring samples back? And this is the reason. Well, the kinds of analyses that we really need to do to answer these big picture questions, the spatial resolution, the precision and the accuracy of analyses that we hope to do, that can only really be achieved by the kinds of analytical arsenal that we have here in laboratories, the state-of-the-art equipment that we have here in laboratories. We have access to, of course, unlimited analytical tools here on Earth, which can be applied to these samples. The size, the mass, the power requirements for these instruments are no limitation. Of course, spaceflight, there are instruments, the size of city blocks, like synchrotrons, that we want to be able to apply to these samples that will never fly. And so we hope to be able to bring these samples back so that we can analyze them with the best possible techniques that we have available here on Earth. And of course, there are a lot of these techniques that rely on complex sample preparation that we cannot, of course, carry with us to other places in our solar system. And so we want to be able to bring these samples back. Carl Sagan said that extraordinary claims require extraordinary evidence. And that's exactly what we're trying to do, is to make fundamental discoveries like evidence of past life. And that's something that we have to be able to confirm. And we can only really do that if we bring those samples here and can replicate those analyses with measurements in multiple laboratories. And so that is really a key factor in trying to bring these samples back. And then, of course, careful curation of these samples will allow multiple generations of scientists to analyze these samples using tools that have not yet been designed or even dreamed of, and asking questions that we haven't even thought of at this time. And so this is going to be an incredible resource for future generations. So what is the big picture value of Mars sample return? This is an incredibly ambitious and bold mission that's going to bring back samples of rock, soil, and atmosphere to Earth for detailed study here. It is of national and global significance, of course, because we have these incredible collaborations. NASA and ESA are going to be working together to bring these samples back. And a lot of the NASA centers are involved, of course, in the various aspects of Mars Sample Return Program. And it's going to pave the way for humans to explore Mars as well. So there's national pride, there is global impact to this mission. There's, of course, inspiration and impact that is going to be fostered as a result of this particular mission. It's our nearest term opportunities, I already mentioned, of answering the question, are we alone in the universe? And it has the potential for really changing our own perspective on our existence. And it'll inspire the boldness of it, the ambition of it. It's going to inspire future generations to come. And I'm sure there's kids over here that are going to be excited to see this mission launch and bring back these samples. And it's going to be a gift that's going to keep on giving, as we say about many sample return missions. You probably heard that from other speakers as well. And of course, it's going to address world-class science, decadal science, meaning that it's going to be responsive to what the national academies, which is the scientific body in the United States that sort of determines science policy and questions that are important. The Planetary Science Decadal surveys basically is a scientific consensus, as close to a scientific consensus as it can be. And the last two Planetary Science Decadals have deemed the Mars Sample Return Program to be one of the highest priorities. And so that's why we want to be able to bring these samples back to be able to answer those high priority questions that I've already mentioned before. And so we want to be able to learn about how rocky worlds form and evolve and become habitable, not just in our solar system, but beyond our solar system, as we try to understand exoplanets beyond our own solar system and in other parts of our universe, and try to understand whether life existed there as well. So, what is the status of the Mars Sample Return Program at the current time? Well, this is, as I mentioned, a difficult and an ambitious program, challenging. It's about as challenging as it can get in terms of complexity and difficulty. And so NASA had tasked an independent review board to assess the cost, the schedule, and the technical aspects of the mission. And this was last year that the independent review board assessed it and provided a final report in fall of 2023. And they determined that this was actually one of the highest priorities, that we should definitely pursue it because it's incredibly important. But at the same time, there are some cost and technical challenges that have to be addressed. And so NASA established an MSR Independent Review Board response team, or the MERT, that basically looked at all the recommendations of this independent review board, and their report was made public just about a couple of months ago. And as a follow-up, NASA is now seeking inputs from industry as well as NASA centers to try to explore options for ways in which we can implement this program in a balanced planetary science portfolio, meaning that we want to keep exploring our solar system in a way that maintains the balance among all of the different targets that we have in our solar system to explore. But at the same time, we want to be able to get to Mars and bring these samples back as well. And so the study reports are going to be due later this fall, and a path forward for Mars sample return is going to be determined by early next year. So please stay tuned for that and look out for some of the upcoming news relating to that. So what I'm showing here now is basically just a notional architecture for Mars Sample Return Program. And it looks complex because it is complex. And I'm going to walk you through it to try to simplify it a little bit. But essentially, the main point I want you to get from this is that the first element of this Mars Sample Return campaign, as it's called, is already underway. Mars 2020, the one that you see on the extreme left side, Mars 2020, the Perseverance rover, that has already launched and is on the surface of Mars collecting samples right now. So it's already happening. And then the next few launches, the next couple of launches, those are part of the Mars Sample Return Program, or the notional architecture for that program. And that is what is being assessed right now through these industry studies and NASA Center studies, and we will have a finalized plan hopefully by the end of the year. And so the plan, as it stands, we start, of course, with the Mars 2020 Perseverance rover, which is, of course, busy collecting a diverse set of samples that represents distinct geologic environments within an area on Mars where it has landed called Jezero Crater, and I'll tell you a little bit more about that in just a second. But that mission is already happening, and we are collecting samples as we speak. And we have the technology at this point to actually go and get those samples. We are collecting the right samples now. So now is the right time for us to actually plan to bring those samples back from Mars. And so this is actually absolutely the right time to be thinking about how we're going to get those absolutely carefully collected samples back from Mars. So Perseverance would actually bring a set of these stored samples that it's been collecting to a sample retrieval lander, which is going to be a spacecraft that's going to land on the surface of Mars, and it's going to carry with it a Mars Ascent Vehicle. And this Mars Ascent Vehicle is going to have a little canister that is going to have about 30 slots in it, and the Perseverance rover is going to transfer the tubes that it has been carrying in its belly, and it's going to transfer them into the sample canister. And then the samples are going to be launched from the surface of Mars into orbit. And this is going to be the very first launch off of any planet. And it's going to be audacious. And it's going to bring back these samples into orbit around Mars, where another spacecraft called the Earth Return Orbiter, which is going to be provided by the European Space Agency, it's going to be waiting in orbit, and it's going to collect those samples in a capture, containment, and return system. And so you can see this animation here, which shows that little basketball-sized shaped canister into this capture, containment, return system. And it's going to transfer this canister into an Earth entry system, which is that capsule that you see on top of the structure. And so the Earth Return Orbiter will then use solar electric propulsion to depart Mars orbit and head towards Earth. And when flying past Earth, the Earth Return Orbiter would then release this Earth entry system, and the Earth entry system would be then targeted to a safe place to land on Earth. And so Mars Sample Return is going to be groundbreaking in more ways than one. It's going to be the first launch from another planet. It's going to be the first in-orbit rendezvous at Mars, which is basically going to be the capture of this canister into this Earth Return Orbiter, and then the first round-trip mission to another planet. It's also going to be the first return of samples from another planet. We, of course, brought samples back from the moon, but that's a small body, and we're talking about a planetary body at this point. We're going to be bringing back samples from this other planet. So Mars Sample Return, as I mentioned, is already underway. It's happening now. The 2020 Perseverance rover is collecting and storing samples of rock, soil, and atmosphere in a region of Mars called Jezero Crater. And this rover, of course, if you're familiar with the set of instruments that are on board, it's a very sophisticated laboratory that's really on board this rover. And you can see the graphic here, which shows the various instruments that are on board this rover. The first one that I'll talk about, this is the Mastcam Z panoramic cameras. This is the eyes of the rover, and they're sending back these beautiful panoramic images of the surface of Mars, and it gives us the geologic context of what we're going to be collecting. We've got, of course, the SuperCam laser microimager, and that's actually a laser. How cool is that? It actually shoots rocks with a laser, and we can get a chemical composition for that rock by looking at the plume that's released from the rock when you shoot a laser at it. So the other instrument that is being utilized, of course, is the Sherlock instrument, which is, you can see, it's at the end of the arm of the rover. And this is an ultraviolet spectrometer that actually looks for organic compounds in the rocks that are being investigated. There's also an X-ray spectrometer called Pixel that's also at the end of this robotic arm. And that's actually, it gives us the chemical composition, the mineralogy of the samples, the mineral composition of the samples in detail. We've also got RIMFAX, which is the subsurface radar, which tells us something about the subsurface structure that we're on. The META is a weather station, which tells us something about the temperature, the ambient temperature, as well as the ambient winds, et cetera. And then MOXIE is actually a technology demonstration package that produces oxygen from CO2. And so that's going to help, of course, when we are starting to think about human exploration in the future. So these, of course, these tubes that are shown here, those are critical for bringing the samples back. So what are we doing in terms of, the tubes that we're carrying on board this rover? Well, there are 43 tubes that are on board the rover. 38 of those tubes are meant for collecting rocks and regolith, and 5 of them are what we call witness tubes. Those witness tubes are actually really important. They serve as blanks. If you're familiar with any kind of chemical laboratory, you have to have those blanks to be able to tell whether what you're measuring is contamination or if it's an actual signal. And so those are tubes that are closed or sealed at particular times in the mission and tell us something about the kind of environment that the samples are being collected in and whether there was any kind of contamination that might have been carried along with us from Earth. And the sample tube, of course, you can see on the left-hand side here what it looks like. And in terms of its size, it's about a centimeter in diameter. And the length of the tube where the sample resides, it's about 6 or 7 centimeters. And so the largest rock core that's collected, it's between 6 and 7 centimeters and about 1 centimeter across, so about the size of a piece of chalk. So that's what we've been collecting on the surface of Mars so far, are basically filling these tubes with these samples. This is then our field site. This is where we are on Mars. This is a topographic map of Mars where you can see the lows are the blue colors and the highs are the red colors. And you can see also labeled here the sites where all of the different landers and rovers have been on Mars in the past. And there's some actually that are shown for the future, like ExoMars, which is going to be a future landing site. But you can see in circled in red the location of the Mars 2020 Perseverance rover here. And here's a close-up of that region. This is Jezero Crater. And you can see here on the left-hand side, there's a little river-like structure. It's a river channel called Neretva Vallis. And this is an inlet valley where we think a river-like feature flowed into this lake that was in Jezero Crater. And there's a little delta that you can see. There's inside of this sort of black kind of ellipse that's shown here, which is the landing site for the Perseverance rover. You can see on that frame there the delta, the river delta that was basically formed as a result of the stream that flowed into this crater and formed a lake. And so this is an environment that basically records riverine features, it records a lake, and so potentially has habitable environments where we can look for evidence of past life. So this site is one of the best preserved ancient lakes on Mars, one of the best preserved river delta deposits on Mars. And this is why it was chosen, because it records those features, and we have the best evidence of being able to find evidence of ancient life there. It provides also a window into early planetary evolution, older than about 3.5 billion years. So the deposits that are within the crater, we think, date back to somewhere around 3.5 billion. The area around Jezero itself has ancient crustal rocks that date back to perhaps older than 4 billion. And so if we go and study these rocks, we'll learn a lot about planetary evolution, early planetary evolution, that is not recorded or that we cannot access here on Earth. And then, of course, there's a diversity of habitable environments here that are recorded. I mentioned river-like deposits from delta. I mentioned the lake types of environments. There's also near-surface water that's altering some of these ancient crustal rocks. That's another kind of habitable environment. There are some hydrothermal features that we think are present here that is yet another kind of hydrothermal another kind of habitable environment that could be recorded in this particular region. So the things that are actually recording these different environments, these are the rocks in this region. And we have a variety and a diversity of rock types in this region, which is really key to answering all of the kind of fundamental questions or the high priority questions that I mentioned early on. So you've got igneous rocks that formed from solidification of magma. These igneous rocks actually form the floor of the crater, of Jezero crater. And these rocks not only are going to be able to tell us something about what the composition of magmas was, or something about the interior evolution of Mars as a planet, but they also record later alteration as a result of interaction with near-surface water. And so that's another kind of environment that is going to potentially tell us something about the possibility of ancient life on Mars. And then, of course, there are the sedimentary rocks, which are the fine-grained mudstones that we find at the front of the delta that we see here. And these are perhaps the kinds of rocks that are going to be the best places to preserve evidence of biosignatures, evidence of past life, microfossils perhaps. So these are the kinds of rocks that we want to bring back and study with the highest spatial resolution electron microscopes and microprobes that we have here on Earth. And then, of course, we've got coarse-grained clastic sediments that are at the top of this delta that record high-energy river deposits. And this is another kind of potentially habitable environment, but they also have a variety of clasts that are brought in from beyond the crater and are basically recording the ancient crust of Mars, which could tell us, again, about early planetary evolution of that planet. There are carbonates, and carbonate is a rock type found on Earth that's deposited in deep water and also preserves evidence of biosignatures here on Earth. And so those kinds of rocks, again, are of great interest from the perspective of being able to look for biosignatures. And then, of course, I also mentioned ancient altered crust beyond Jezero crater. That's going to tell us a lot about early planetary evolution, as well as possible habitable environments beyond the crater. So this is then the field site from an orbital, high-resolution orbital image. You can see the region that's labeled as the crater rim. That's a little bit raised, and you can see one portion of the crater rim right there. And you can see the riverine feature here, the Neretva Vallis, which is the river channel that flows into the crater. And you can see the delta formation there, labeled as the western fan here. And then, of course, the crater floor, which is made up of these igneous rocks, which are formed from solidified magma. And the star there is the landing site for the Perseverance rover, and that's where we landed and started the exploration of this region. So what have we been doing so far? We've been on Mars at this point with Perseverance rover since 2021, early 2021, and we have been investigating the different regions of Jezero crater in these science campaigns. There's been the crater floor campaign, where we've collected 10 samples, and then we've investigated the delta fan front, where we've collected 11 samples, and then we've moved on to the upper fan, or the upper portions of the delta, and we've collected 3 samples there. And now we are at the crater margin. We're approaching the rim of the crater, and we've collected 3 samples so far. We might collect a 4th one relatively soon, within the next month or so. And then we're moving on to the next portion of the science campaign, which is going to be just at the crater rim and just beyond that. And so that's what we're looking forward to in the near future. So where's Perseverance right now in terms of the field site? And so this map here now shows, again, an orbital image that shows the landing site is on the lower right-hand side, And the white trace that you see from the lower right-hand side extending up, going up to the upper left-hand side, that's the trace, the path that Perseverance rover has taken since it landed, and then exploring the different portions, including the crater floor, the fan front, the upper fan, the crater margin, and now you can see the blue dot on the upper left, which is where Perseverance rover is right now. And then, of course, you can see the green dot there, which is the Ingenuity helicopter, which you may have heard of course. It has a broken wing at this point, so it's not flying anymore after 72 flights, which is an incredible, incredible success story because it was only meant to fly about 5 or so. And now, after so many different exploration and sorties, it finally had to, it's finally now at its resting place. It is still actually collecting images, though, and those images will, at some point, perhaps be transferred to us as well, so it's still going. So Perseverance is at that blue dot, as I mentioned, near the crater rim, and at the current time, we've collected a total of 27 sample tubes have been filled. And of these, 21 of them are filled with rock cores. There are 2 that are filled with what we call regolith. Regolith is basically just a mixture of fine-grained dust and particles and rock clasts that were collected from one of the sand dune-like features on Mars. We've got 1 sample tube that's filled almost entirely with Mars atmosphere. We've got 3 witness tubes, since those are the blank tubes that I mentioned before. One of the things that we did very deliberately as part of the campaign, the crater floor and fan front campaign in particular, while we were first exploring Jezero Crater, was to actually collect a duplicate sample for every rock that we studied. And that was a deliberate strategy because we wanted to put down one of those duplicates in a sample cache that was a contingency cache, in case there was some kind of emergency, in case there was some kind of problem where we were unable to access the samples on board Perseverance, we would have a place where we could actually go and get those samples back. And so we had a duplicate sampling strategy for the first part of the mission. And so 10 of those sample tubes are now sitting in a cache called Three Forks in a location that's very close to where you see the label for fan front. So the Three Forks depot has 10 samples in it. And on board Perseverance, there are now 14 rock samples, 1 of the regolith samples, and 2 of the witness tubes. And so we've got these samples now sitting on board Perseverance. And of course, Perseverance has a duplicate of all of the samples that were put down in the Three Forks depot. And it's been collecting samples since then. And so the cache on board the rover is getting better all the time. And that's the sample set that we want to bring back eventually. And so right now, we have something like 14 unfilled tubes, and there are still something like 12 sample tubes that we're going to be filling with more rocks and regolith, and 2 that are witness tubes that we're still waiting to seal. So just going to tell you a little bit about each of the different science campaigns and the rocks that were collected there and why I'm excited about some of these rocks. The crater floor campaign, I mentioned that we collected 10 samples, and here are the tubes sort of represented here. One of them is a witness tube, one of them is an atmosphere tube, and then 8 of them are basically igneous samples, 4 of which are what we call basalts, meaning they're made up of these minerals called plagioclase and pyroxene. 4 of them are another kind of igneous rock called olivine cumulates. And these rocks, all of them, actually have in them salts such as sodium chloride or sulfates, things that were deposited by near-surface water circulating through these rocks after they solidified from magma. And so they actually do record evidence of liquid water flowing through them as well. So these are going to be an incredible set of samples that we're going to learn a lot about what Mars was like in its interior, the chemical composition that melted to produce these lavas. We're going to be able to date these rocks potentially and be able to learn something about the time frame of when this volcanism was happening. We're going to be able to study the salts in these rocks and be able to learn something about the composition, the chemistry of the water that was flowing in the surface. There might even be some record of some kind of biosignatures in them. There might be organics recorded in those salts, but we have to bring those samples back to be able to detect those really with the precision that's going to be needed. Here are the close-ups of two of those types of rocks, just as an example. So as I mentioned, we collected duplicate samples for all of the rocks in the first phase of the mission. And so there, you can actually see in the image that you see in the middle, bottom image, there are two holes that you can see, and then there's a little circular abrasion patch. And so for every rock where we're sampling, we actually create a little, we grind down a patch that's about 5 centimeters across, called the abrasion patch, and then we do contact science at that abrasion patch and learn something about the rock chemistry, the rock mineralogy, and then we collect the samples of the cores. And so the two holes that you see in that rock, that's where we collected the cores. And you can see on the right-hand side there, the tops of the sample tubes before we sealed them. And so you can see the tops of those rock cores that were collected. And you can see some of the salts. The white things are the sulfates and some of the sodium chlorides and things like that that are actually preserved evidence of water that flowed through these rocks after they solidified from magma. And so this is actually just an X-ray map showing part of the abrasion patch, which actually shows some of the interlocking texture of the two key minerals that tell us that this is a basalt, plagioclase and pyroxene, the green and the purple minerals. So this interlocking texture that we see, this is a very characteristic thing that we see in basaltic rocks. And so we can tell with a fair amount of certainty that this is exactly the kind of basaltic rock that's going to tell us a lot about the interior composition of Mars, et cetera. These are the next two campaigns, the fan front and the upper fan. And the samples that were collected, the 11 samples that were collected at the fan front and the 3 samples that were collected on the upper fan. And these are the sedimentary rocks that were actually deposited in either a lake-type environment or in a river-type environment. And so on the extreme left-hand side, you've got these 2 medium-grained sandstone samples. And then in the middle, you've got the 5 mudstones, very fine-grained samples. And those mudstones are really I think they're going to be really exciting samples to look at, because those are the ones that are going to preserve possibly evidence of potential biosignatures. The Sherlock instrument, actually, there might be detection of organics in these rocks as well. And so it's going to be exciting to bring these back and really be able to study them in laboratories here on Earth to confirm whether we do see evidence of those organics and other potential biosignatures in these rocks. The Crosswind Lake and Atmo Mountain, those are the 2 Aeolian regolith samples. And those are really going to be very interesting because they're going to tell us something about the composition, not just the composition, but actually even the physical characteristics of airborne dust as well as fine-grained particles on Mars. And it will have implications for understanding hazards to human exploration as well. And so we're interested, of course, to understand the chemistry of these samples and learn something about the source materials of these clasts that are going to be found in this regolith. But it will be hugely important also for enabling us to plan for human exploration in the future. And then, of course, on the right-hand side, the upper fan samples, those are actually coarse conglomerate samples. And that's kind of a mixture of rock clasts that came possibly from other places beyond the crater, beyond Jezero crater, was carried in by this river that brought in these materials and deposited them in that delta. And so we're going to be learning something about places on Mars that are way beyond the crater that we're in right now as a result of studying and looking at these little rocklets that we find inside of these samples. Here are then some close-up examples of the rocks that we're going to be investigating. This is actually one of the mudstones, very fine-grained sample. You can see in the abrasion patch that's right in the middle that it's extremely fine-grained, and you can see those white things that traverse across the sample. Those are the sulfates, the salts that are deposited in this rock, again, deposited by liquid water at some point in the past after this mudstone was deposited. And so this is going to have multiple generations of salts preserved in this rock that are, again, going to tell us something about the chemistry of the fluids that were flowing through this rock. It's possibly going to tell us something about biosignatures that might be preserved in these samples. And we're going to learn a whole lot. That's going to be super exciting for us to really try to understand something about ancient possibilities of ancient life being preserved in some of these samples. Here's just basically a little animation that shows, actually it's not an animation, it's the real video showing the regolith being collected from one of these sand dunes. And the bit that's collecting the regoliths is different from the bit that collects the rocks. And you can see on the top right, the top of the tube that's showing the fine-grained dust and other fine-grained sand that forms this regolith, along with some of the rocklets that are present in this regolith sample. And so again, this is going to be really, really important for us to understand the chemical, physical characteristics of the fine-grained dust in this, which is going to, again, have implications for the kinds of things that we have to worry about when humans are going to be exploring Mars in the future. And then, of course, the conglomerate sample. This is an example, again, from the two campaigns that I mentioned before. This is the top right. You can see the top of the sample again, and it's like a little jewel box of little gems, individual clasts that are coming from different places on Mars, carried through the river that's coming into Jezero Crater and deposited on that fan front. And cementing that together are some salts and other things that, again, are recording the kinds of water that was flowing at the time. Lastly, the last campaign that we have been investigating, of course, is at the crater margin. And here we've collected, as I mentioned, 3 samples so far. And these 3 samples, there's some disagreement at this point in the science community about whether these are sedimentary rocks, whether maybe these might be pyroclastics, perhaps. But we don't know for sure. But what we do know is that there are cements in these rocks that were deposited, again, by water that are made up of carbonate mineral and are made up of silica. These are both phases, carbonate and silica, that on Earth, when we find them, this is where we find the best evidence for microfossils and other types of biosignatures. And so this is going to be, again, these are going to be super exciting rocks to investigate. And here's a close-up of one of these samples. And you can see here on the left-hand side, that's the abrasion patch. You can see some of the clasts that you can see. On the right-hand side is the top of the core that was collected. Again, that's about 1 centimeter across. And it's made up primarily of silica and carbonate, as I mentioned. And it's going to be really, really important and exciting to actually investigate that with the highest spatial resolution that we can get to really study what's in these materials, that we can learn, again, something about the potential for ancient life on Mars. So this is then the final kind of rogues gallery of all of the samples that have been collected so far. And you can see just by looking at the image, the incredible diversity of rock types that we've collected so far. The tube on the top left, by the way, that's an empty tube, meaning, well, it's not actually empty. It's got Mars atmosphere in it. And so that's going to be, of course, important to analyze as well. We want to be able to analyze the chemical, the isotope composition of the atmosphere. We want to know whether there was any methane in that atmosphere. All of that that's going to be super important to analyze as well. And then the ones on the bottom right, those are the witness tubes. And so those are the ones that are the blank samples. And then in between there, you've got all of these diversity of igneous and sedimentary rocks and clastic rocks, and basically the regolith as well that I just pointed out to as well. And so we've got an incredible, fantastic collection. And so the samples we've collected so far, it's a better collection than we had ever reason to expect before we got there. We actually had expected before we landed, we thought we would find only sedimentary rocks inside Jezero Crater, but as it turned out, the crater floor was made out of igneous rocks, and that was a big surprise. So we've got actually better diversity than we had even reason to expect. And so these igneous rocks are going to tell us something about the absolute ages of units in Jezero Crater. There's going to be the potential to anchor the ages of Martian epochs as a result of these samples. We'll learn from the sedimentary rocks about biosignatures, potential biosignatures preserved in these rocks, about habitable environments. The secondary products, the salts that I mentioned in these rocks, those are going to tell us something about the near surface water in these rocks. And then the potential presence of organics, we're going to learn a lot about that as well from studying some of these rocks, especially those fine-grained sedimentary rocks that I mentioned. And then, of course, the samples will be able to address some gaps in terms of concern for human exploration. What's next? I'm wrapping up here pretty close to finishing. This is actually the picture in the middle, the long vertical picture, is showing the rim portion of the crater that we're going to be exploring very soon. The blue dot is where Perseverance is right now, and the white trace are the notional traverses that we might follow. And what I want to just mention here is that there is a diversity of rock types and ages of rocks that are going to be different in the rim than what we've already seen inside Jezero Crater. And so we're now going to be coming up and exploring rocks that are going to be very different than what we've seen before, and they record different environments than what we've seen before. Some of these environments, such as the hydrothermal rocks that we expect to find here, they record different habitable environments than what we've seen before. And so this is going to be super exciting to be able to look at completely different rock types, completely different habitable environments just beyond the crater rim. And so this is going to be my last slide. I'm going to finish up with this quote from Dr. Seuss, which is an exhortation for Perseverance to go and explore beyond the crater rim and to fill up the rest of the tubes with some more exciting samples for us to eventually bring back, and an exhortation for us to really get busy with bringing these samples back. And at the very end, I think I'm just going to go to the last video, which is just 2 minutes, which is going to be showing you how we might bring those samples back.
Wow. Well, thank you for an amazing talk. We do have some time for some questions, so if you're in the audience here tonight and you'd like to ask a question, please make your way to the microphone so that we can get your questions answered. But while we wait for folks to work up the courage to go to the microphone, we do have some questions coming in from online. And I want to combine a couple of them. What we just saw in the video, was very impressive in terms of, the technology of bringing these samples back from Mars. And there are a lot of moving parts, which means probably a lot of technological challenges. What do you think are the biggest challenges that you face?
Well, yes. I mean, it is going to be something that's going to require a lot of coordination and efforts from multiple space agencies, as we mentioned. NASA and ESA are both working together. There's going to be a number of different centers, NASA centers that are going to be involved. I would say the biggest technical challenge is, I think all of the technologies that are required, we are actually at a point where they're all achievable and they're all doable. So, we've actually shown that the technologies are all capable of bringing the samples back as we plan. Not to say that it's going to be simple, but, some of the technologies, for example, as I mentioned, launching a rocket for the first time from the surface of a planet into orbit, rendezvousing in orbit around Mars. Those are all going to be challenges, right? But I think that we're at a point where we feel like we have a handle on them and we can do it. Part of it, of course, is going to be the challenge of also bringing, once we have the samples back here, we will obviously have to make sure that we are doing a safety assessment of those samples, making sure that we can ascertain. We think there's a very, 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 very low probability that there's any evidence of extant life. What we're looking for in these samples is evidence of ancient life on Mars, the kind of environment that these rocks are being collected in. We don't think there's any possibility really of extant life. But at the same time, in the abundance of caution, we are of course we're going to be very careful about making sure that the samples are safe to then release to laboratories across the world to do them. So there's going to be a lot of firsts here. It's going to be challenging, but NASA has shown through many other prior experiences that can rise to the challenge, and certainly ESA is very committed to it as well. And so yes, we feel confident we can do it.
So challenging, but also incredibly exciting.
Very exciting.
And I understand we have a few folks at the microphone, so we'll take a question from the audience.
Sure. Hello. First, I just want to say thank you, Dr. Wadhwa, for your amazing, thought-provoking presentation. And I'm very excited to see in the coming years what comes back from Mars. And my question would be about the Perseverance rover itself. So after, it's done its duty, what's the lifespan left on that after the samples are sent back to Earth?
So, what we've learned from rovers that we've sent to Mars before is that they actually last for a lot longer than we think they're going to. That they certainly last way beyond their design, what they're designed to do. The Curiosity rover, for example, has been exploring Mars for over a decade now, and it's still going strong. The prime mission, of course, was only very short compared to what it's doing. So the expectation is for Perseverance to be exploring, for at least another, more than a decade, and then beyond that, the hope is that it's going to be able to continue working for a while, but we'll see how that goes. But I think, the hope, of course, is to be able to bring these samples back, perhaps within the horizon for that is, again, we'll have to determine exactly when that'll happen. It'll be hopefully in the 2030s, and so we certainly expect Perseverance to last beyond that time frame.
Perfect. Thank you so much.
It's really very remarkable, right? With Spirit, Opportunity, Curiosity, Perseverance, we've had 20 years of continuous roving and exploring on the surface.
Exactly. It's incredible.
Yeah.
These machines are incredible.
Let's take another question from the audience.
Well, I just wanted to thank you for a wonderful talk. Thank you for explaining how rocks rock.
Thank you for that.
Of course. I was just curious, if I understood you correctly, you talked a lot about how the atmosphere on Mars is a lot weaker than the atmosphere on Earth, and that the atmosphere would protect the planets from radiation and debris. If the atmosphere is that weak, how are you able to determine if these samples are affected by the radiation and debris from broader space, and what's the plan to distinguish that?
So yes, the current atmosphere on Mars is certainly very much thinner than it was in the past, and yes, the current surface of Mars is highly irradiated as a result of that. Much more so, of course, than the Earth's surface is, because Earth has 100 times thicker atmosphere. And also, of course, I mentioned the magnetic field. That has a lot to do with preventing kind of the irradiation of the surface from solar wind and cosmic irradiation. And the current surface of Mars certainly has been irradiated by that too, because the magnetic field on Mars at the present time is very, very weak. In the past, it was not so. So I think the interesting thing there is to say that the current conditions on Mars, especially within this area that we're exploring now in Jezero Crater, those are not hospitable for life or anything of that sort. But in the past, it was very different. And so the rocks are really, the rocks rock, as you said, right? I mean, they are recording the history, the past history that these rocks have seen, the kinds of habitable environments where the atmosphere might have been thicker, the magnetic field might have been active, there might have been liquid water on the surface. All of those kinds of conditions, the chemical conditions, are recorded in these rocks, and we can still read that record. Using the amazing technologies that we have here on Earth, we can actually still read that record. And so that's what's going to tell us about whether there's going to be evidence of ancient life. Some of the biosignatures, such as microfossils perhaps, that might be preserved, or even organics, those could still be preserved in those rocks. And things like the silica or the carbonate phases that I mentioned. So yeah, I mean, I think that's why we want to bring them back, is because I think remotely it's very difficult to actually measure those things, but when you bring them back in laboratories, you can actually do it really well.
Definitely, I think the significance is really exciting, but I'm not sure if like the radiation would react with some of the chemicals in the rocks and like change their composition.
Yeah, so I mean, I think if that does happen, some of those effects might be at the very sort of top layers of the rocks, and we're actually collecting 7 centimeters down for most of these materials. And so, we really don't think that, understanding some of the effects of radiation, we actually do understand some of those effects, and we don't think that that would have actually fundamentally changed the chemical makeup of the rocks and what's preserved in them to a great extent.
Thank you.
Well, unfortunately, that's our time. But if you still have questions, please stick around after the talk, and Minnie will be happy to answer some of your questions then. But in the meantime, thank you all for coming here for this lecture. And for those of you who came for the whole series, thank you very much. I think we put together a pretty good program this year. Unfortunately, we won't have any stargazing tonight because of the weather. So you'll have to wait for a better night for that. But I want to thank our sponsors again. Thank you to the United Launch Alliance and to Aerojet Rocketdyne for their support, and congratulations again on today's successful launch. And again, thank you to our speaker, Meenakshi Wadhwa.